Hey guys, welcome to the third video of this series. In this video we're going to be working with attractors. Attractors is a great way to jump into Grasshopper, and it's quite common for it to be part of an early introductory series in Grasshopper, so I'm sure you'll see a lot of it throughout this semester. To give you an idea of what attractors are, let's just do a quick Google search. I'll just type in Grasshopper attractors. Attractors is the idea of using a point or a curve and measuring the distance between one from the other and using that to then determine whether that surface or pattern changes scale, rotate, has a different height, or basically anything you would like it to do. So for example, this image here shows a series of cylinders, and what you can see is a squiggly negative space, which would be a curve attractor, like in this image. For this exercise, they've drawn a curve and they've said that every cylinder that is closest to this curve will be the shortest and the smallest in diameter. And as you move further away, you get taller and the diameter gets larger. So let's open up Grasshopper and Rhino, and let's double click on the canvas. And let's type in and create a rectangular grid. So type in rect, find the rectangular grid, which looks like this. Put it on the canvas. Okay, so this grid has a base plane, which is the center point. In this case, it defaults to XY, which is located at the origin, and that's fine. We can determine the size of the cell, this single rectangle being the cell. All the rectangles together is the grid. So let's say we want 0.5 and 0.5 for the X and Y. Make it a tight grid. And the number of grid cells, at the moment the default is 10 in the X and 5 in the Y. So let's just go make a slider for 10 and do that for both inputs. So now we have a nice square grid with square cells. Next, we need a point, and the point is what we're going to use as the attractor. So double click in Grasshopper, type in point, and select the point container. And for this example, I think we should work with a point in Rhino, so that way we can move it around and play with it dynamically. Your toolbar is probably down here on the left. I've moved mine up the top. Either way is fine. Find the single point, left click, and click it anywhere in the Rhino canvas. And then come back to Grasshopper, right click, and set one point, and then click the point. So we've now created a link between this container and the Rhino point. Okay, so to work with attractors, we basically want to work out the distance of our floating point that we can move around to every other point in this grid. So what you can imagine will happen is we're going to be drawing with Grasshopper a line between each point, and then we're going to be measuring the distance of that line and using the numbers of that output to control a series of operations. Okay, so we have our points for the center points of our cells, and we have our floating point. Now let's double click and type in distance, and what we're going to do is we're going to take these center points, we're going to right click on A and flatten the data, and then we're going to put into B our second point. If you hover over the output, you see a series of numbers, which are the distances between point A and B. Now, double click and type in panel, and hit enter, and put the centroids into a panel. I just want to show you why I've done this flatten. So at the moment, these points are in a data structure that are basically in lists of 10. So we have 0 to 9 which is point 0 is this lower left point, all the way up to point 9, which is the 10th point in the list. And so basically, this component organizes our points into columns, and that's done by a data structure. So 0, 0, 0 is the data tree, which represents this column. 0, 0, 1 is the second column, so on and so forth. And then indices 0 represents the first point of that tree. Indices 0 in this tree represents the first point of the second column. However, we just want to be able to create lines between this point and every other point, and we don't want it to be in groups. So what we do is we flatten it, and I'll actually do it on this side, so you can see that now we've taken out the columns and we just have one long list of points from 0 to 99, which is our 100 points that we can see on screen. And then while we have a panel here, let's take our distance output and plug that in. Now you can see we have distances as long as 6 meters and as short as, 1.5. Now, to make these numbers usable, let's say we want to scale the size of these cells. To try scale a cell by 6, it's just going to become incomprehensible. So what we need to do now is we need to remap these numbers, or these distances, to a new minimum and maximum that we can use. So let's double click and type in remap. We have remap numbers. Take our distances and put them into V for the values to remap. S input asks for the source domain, so let's double click and type in what we call bounds. The bounds allows us to get our minimum and maximum number from a list. So if I put in D distance into N for our numbers, hover over the output, and you can see that our minimum number is 1.19 and our maximum is 6.24. Let's put that input I into S. So more often than not, you'll probably use or see the remap and the bounds used together. The last input we need is a target domain. So by default, we have 0 to 1, which is fine, but let's just create our own domain anyway, so you know how to do it. Let's go to Math, Domain, Construct Domain. Put in our input to I, and again by default we have a 0 and a 1, but what I want you to do is double click and press 1.000. What that does is gives us a slider between 0 and 1, but with a floating point, so we can go down to as little as 0.001. That's going to be our min, and then we're going to Control C, Control V, and put it in as our max. I'll make the start number low, the large number a bit higher. And now let's scale. So double click, type in scale, click that one there, and have a look at the inputs. So it asks for the base geometry to scale, and that's going to be these cells. And let's flatten those to put them into a single list. The center of scaling is going to be the center point of each square, so it's going to be C. And now you can see we have 2 lots of squares, and I'm just going to come back and turn the preview off for those 2. And if I hover over the third input for our scale, it's asking for the scaling factor, and by default the scaling factor is 0.5. Basically what that has done is it's taken our initial grid and halved every square, or scaled it by 0.5. Now if I take this list of numbers that we've just remapped from being a series of distances in meters that go as far as 6 to now a series of numbers that are between 0 and 1, being 1 being as big as they can get before they start to overlap or intersect, and 0 being non-existent. We now plug that input into R, turn that initial grid off, and you can see that we have furthest away from our floating point a relatively large square, and closer to it quite a small one. Now that is what you would call our min and our max, controlled by our minimum and maximum domain numbers. So if I change this number to be quite small or to 0, the closest is disappeared, and if I change the furthest, I can change our maximum number and increase that to 1, and so you get a full square at the furthest point and anything in between. So you can do the inverse by swapping the numbers. You can make them change dynamically. And so the point of an attractor is that you can now get this point and move it around, and everything will attract an update to it. Let's change the scale of our grid so we have some more squares to look at. We can do that by changing the size of the grid and then the extent of that grid. So let's just make that 20 by 20. Got there in the end. Okay, so we have a smaller grid, finer resolution, might even go a bit tighter, and I can play with these numbers. Cool. Alright, so a few things we can do from here just to play around before I move into another attractor exercise is we can turn these into surfaces. So if you double click and type in boundary surface and put your G output for scale geometry into the input, we now have surfaces, and that red is just showing how long the process time took to compute. Something else that could be interesting is to turn this back on, our initial grid. And now we can look at that as a potential facade where you have a frame as the exterior panel and then glazing on the interior. Let's try that. Let's double click and type in loft. Let's just make a quick change to what we have in order to set up the data structure correctly. So let's change that flatten and make that flat on this side. And let's go and find a graphed tree. So what we've done here is we've flattened our list so everything is on its own index item, and we only have one path. So we have 0 to 399. If I put that into a graph tree and show you what that looks like, I now have every index at item 0, and the data path structure increases by 1. So we're going to do the same for our scaled items. Now it's important to make sure that the data structure matches to both of these. So you can see I have 400 locally defined values. I have a data path of 00 through to 0 semicolon 399, and I have the same on the graph tree below. Now that I'm happy and sure that these two are the same, I can put them both into my loft. Connecting the first one, then holding shift, pull out the second one and connect. delete this, and I'll delete this. And I'm going to turn everything else to preview off. So now you can see the facade taking shape. I can move this around. I actually think that they're a bit small to be windows, so let's make our minimum value slightly larger. You can kind of look at this as a series of openings, windows on the side of a building. And so you want it to be somewhat larger so we can actually get some light in. Maybe make the bigger ones bigger. And let's have a look at that in Rhino. So I'm going to right click and hit bake. And for now I'm just going to bake it to the default layer. And then you can close Rhino and double click your perspective window. If yours is up here, just double click it. And now just have a little look around at the panels. So Control Z to undo the bake, type in Grasshopper, bring up our window, and I'm just going to select everything, right click and hit disable. So that way it doesn't slow down our window, but we can save it to come back to later, especially if you want to look at it as a resource. Double click, press Shift and the squiggly button under the escape. I should really learn what that's called. And type in attractor point, rectangular grid. Okay, let's work on the next exercise. Let's go back and add another point here. Go scaling. So we know that this attractor uses the scale, and I might actually get you to go and select it and hit Control G. We're going back through now to label and organize our code. So we can right click on the group and type scale, Control G. We can say let's say window frames, and this guy here, let's say that's our attractor point. Okay, I'm going to get you to select everything, Control C, Control V, bring that down, and we can delete the last 4 components. Delete them before you enable, so it's nice and quick, and then you can enable it. What we're going to look at now is a similar exercise, but we're just going to use our remap values to change the height of the rectangles. So that's a move translation. Type in move. We're going to move in a direction. So T is the translation vector. So we can go to the vector tab, look at the vector drop down and find unit Z. So we're going to move these up. And G is the geometry to move. So I'm going to take the C, or the cell output, put it into G. I'm going to use these values as our factor to tell Grasshopper how much to move each square by, and I'm going to put that into T. So now we have more of a three-dimensional result, where that point can be shifted and is dictating the lowest point on that surface. Again, let's boundary surface that so we can preview it nicer. If you want the inverse, you just make your minimum number higher and your maximum number lower. So that's saying the line that is the shortest between the 2 points should actually push that or move that surface furthest away. So you can see that if I turn on these points, we have those two being really close, And now we've set up an inverse relationship where that actually pushes our faces further away. And we still have our attractor point. Select it all, disable, and Control C, Control V. Let's label this attractor point, rectangular grid, and height change. Select it all, Control C, Control V, bring it down. Delete the last three. Right click, enable. Let's try rotation. Okay, so let's put down a rotate. It asks for the geometry to rotate. We'll turn them into faces again so we can see them. Take our cells, put it into a boundary. That's our geometry. The angle that we're going to rotate is going to be the angles, the numbers coming out of our remap. If I turn this off and disable the preview, you can see it's already doing something, but it's kind of a bit wacky. It's not really working. That's because we still have one more input, which is our rotation plane. Let's rotate the panels in the X and Z direction. So at the moment you can see on the ground there's a plane there, which is representing XY. We want to make a plane that is within the XZ. So let's type in XZ. Let's take these points, put them in the XZ, and they're the planes. I'll just change that display. So you can actually see the little planes. Make them smaller again. One sec. So that represents the plane. That's basically what we're seeing in the Rhino viewport. It's called a C-plane. When we draw, it's always going to be fixed to that plane. Same here. We're basically taking these cells and we're going to say let's orient them or rotate them on that plane. So we've now shifted the plane that we're working on and put that into P and turn the preview off. So now you can see another three-dimensional surface controlled by that point. It's controlling the rotation or the opening of these faces. We can make that a little more exaggerated by maximizing these numbers. And let's right click and hit bake, bake to default to get a better look at it in Rhino. Control Z to undo the bake to Rhino. Type in grasshopper. Select it all, disable, Control G, rotate planes. And let's change this name to rotate planes. And for the very last one, let's copy everything, Control C, Control V. We're going to do a rotate axis example. We can delete the rotate plane, enable everything, type in rotate 3D, and you can see the difference between these two is that it now asks for an axis of rotation. So instead of a plane, we need to generate a line as an axis. Our geometry is still going to be the same panels. Now we're going to create a line between our floating point and every point on the grid. And we'll put that into X. That's pretty funky. Center of rotation is going to be the center point of the grids, and the amount of the rotation is going to come from our remapped values once again. Let's turn the lines off. And again, we have a similar result to the previous one, but now we're rotating in multiple axes rather than just the one. And let's bake it again. This time to bake, just select it and hit insert on your keyboard as a quick way to. Alright, thanks guys, and I'll see you in the next video.